We're not machines. We're people. This is the desk of Ladyada.
But we like talking and making machines. So
Robot friend.
Yeah.
Yeah.
It's machine and human peaceful coexistence time here. Desk of Ladyada. I'm Ladyada. Welcome to my desk. With me is Mr. Ladyada, who he speaks for the machines.
I'm machine friend, not machine enemy.
Yeah. And tonight I thought I would take some more time to play with i2s microphones. Boy, we really love digital microphones here at Desk of Ladyada. It's been about a week of digital microphone joy. And I thought I would try something that I was, curious about, which is the i2s microphone breakout that I made to test with the SAMD processor. Could I get it working on a Raspberry Pi? And I'd used i2s outputs, but I hadn't used i2s inputs. So I thought that would be kind of interesting to go through and learn how to do that. And boy, did I learn a lot. So I spent a couple hours yesterday figuring that out. And I thought I would show you the process. Luckily, a really nice person on the Raspberry Pi forums figured out a pretty good step-by-step process on how to do it. It's not super easy, but with a little effort, you can get it done.
Okay.
Okay.
So what do you want to show first?
Well, let's go to the computer, and I'll just show off the i2s microphone. So this is the board for the i2s microphone. It's really small. This is a little sensor, and we showed it on the microscope before. This hole here is the audio port. So it's actually bottom mounted, and you'll see on the PCB the hole goes through the PCB, and that's where you get audio into. And then you've got a bunch of digital pins, and because this is bottom mounted, this is reversed. So let me flip this. Think. And now
Did you just flip a chip?
I just flipped the board. So you get 3-volt power, ground, bit clock, so that's the data clock, data out, WS, which is word select, left or right, and then cell, which is actually tells the microphone which word select bit to listen to, and you'll see that shortly. So this is just an i2s mic. There's a couple different versions. This one is the SPH 0645. It's got a 20 hertz to 20 kilohertz reaction range, frequency response range. We got it working with the Feather M0, but I want to try it with a Raspberry Pi. Because Raspberry Pi, it's actually, even though there's a lot of audio output options, right? There's HDMI audio output, there's the 3.5 millimeter jack audio output, and then you can set up i2s audio output really easily. And there's like 15,000 hats, bonnets, whatever options that you want to add onto your Raspberry Pi for i2s audio out. But what if you want audio in? And this is something that's come up a lot lately because people are making their own like voice agents, because like the Alexa core was released for Raspberry Pi. So having a way to get audio in is really good. And the nice thing about i2s mics is they have pretty good dynamic range, so like even if you're far away, I think that the software will be able to bump the gain on it and get enough data out of the signal to recognize your voice even if you're not very close. Although so far I've had to be pretty close to test these mics. So let's go to the overhead, and I'll just show how I wired this up. So here I've got my Raspberry Pi. Oh, yeah. Hold on. Here I've got my Raspberry Pi, and I'm actually not using this cobbler here. This is actually the microphone here, and I've got it wired up. You can see it's there's jumpers going to the 40-pin connector, and so there's power and ground over here, and then I think bit clock is here, and then the left-right select is here. And data in is there. So there's a pin that's used for the i2s audio out, and then you'll reuse the clock pins and then just use the data in pin for your microphone. So this is your microphone. And so you can see with the microphone it's upside down because the hole, which is right there, is pointing out. Okay, so let's go to, let's go to the computer. And so I was kind of like, well, let's Google around and see what I can find. So I actually have a tutorial on how to use like one of these USB audio cards, and this actually works pretty well. You can use a USB audio card and it has audio in. You just connect a microphone, and this works great if you just want to do that. And then this person, hold on, I think their name was Audio Badger. They're the best. Let me find Audio Badger.
Third cousin to Privacy Badger.
I know, right?
But I didn't want to say it.
Yeah. Thanks to Audio Badger, who has a cat icon. Get out of the way.
Meow.
Meow. Yeah, cat. This person, like, actually got a like step-by-step procedure on how to do it. And so, here's the interesting thing about i2s audio input. So, i2s audio output, there are drivers in the Raspberry Pi kernel that are pretty much all set up, and like i2s audio is pretty much simple. Like you take the audio data and you just send it and you clock it out. Microphone isn't that much more complicated, but for reasons I don't completely understand, they didn't compile in like a working i2s microphone kernel driver into the Raspberry Pi by default. They probably will eventually. If people start using these, I've noticed they'll be like, oh yeah, we should like compile this in. But until that happens, what you end up doing to get it working is actually somebody wrote like a really basic skeleton of an i2s audio card that does input and output, and then you actually compile it and insert it into the kernel. So this is kind of a neat thing, but like basically, you know, you've got what it used to be like is when you had your kernel, it was like this monolithic code, and you would have like your driver here, and then you'd have like your, you know, sound card driver here, and then maybe your like VGA driver there, and you'd have all of these different driver modules built into your Raspberry Pi kernel, your Linux kernel. But what happened is eventually people were like, well, you know, all of this stuff, this is all in memory. Like, this is all stored completely in your computer's memory. And nowadays, you know, we've got like gigabytes of memory, but in lost olden days, you'd only have maybe, you know, 128 megabytes, 256 megabytes of RAM. And you want to still try to run Linux on something like that, or even embedded processors now, they might only have, you know, 32 megabytes of RAM. Even the first Raspberry Pi only had 256, not that much. And the kernel, if you include all the drivers, because there are like 1,000 drivers, every chip, every like USB sound card, every like audio driver, all these things, each one of these, you know, they'll take up like 100K here, and maybe this sound card is like 240K, and this adds up, and you have to store all of that code in memory to access it at any time. And this is annoying. Like, you don't want to have to load all, I mean, even though it's like swapped out, you don't want to have this, it just got huge and huger and huger and huger, and eventually some people said, okay, well, you know what we'll do? We'll make it so instead of having each driver actually in the kernel itself, we'll have kind of like an asterisk, and we're like, oh, if you need a driver, you can look on the file system and load it as a module. I'm simplifying things a little bit, I know. But the idea was that you'd have this little notch, and you would, if you needed this driver, you could tell the kernel, look, you know, you can load it from the file system, where you can load your own modules as needed and plug them in. They're kind of pluggable modules. And this is how the kernel works now. Now, not all things are modular. Why? Because some things are like absolutely positively required. Like, you can't make them modular. So, for example, the code that handles the file system stuff, you're not going to have that be modular, because like if you can't get to the file system, you're not going to be able to, like, you can't do anything. So that's required. Or the stuff that handles like process control, or the virtual memory stuff. A lot of the low level, super essential things you'll put inside the kernel. You won't have it be a module, because like there is a little bit of code that you need to add to make it modular. So, and also some are like, because they're, you know, maybe they're required before the file system is brought up, you can't make them into a module. But for most things like drivers, like chips or USB devices or whatever, where you want to have them be modular, it's pretty easy. And in fact, one thing that I don't do very often, because I keep forgetting you can do, is after the kernel has been compiled and even loaded, you can hot swap kernel modules in and out, which is kind of, well, it sounds kind of ridiculous until you think, well, you know, like that's what Windows and Mac does, right? When you have a Mac or Windows computer and you plug in a device, right, it goes da-dunk, and it goes and finds the driver for you and loads it into the kernel for you. And in fact, in Mac, you can look at the KEXTs, I don't know, it's like extension. Basically, they're modules, like little chunks of code that you can bring in and out of the kernel as necessary. So you don't end up having this huge, like crazy blob with 10,000 billion drivers. You only have the ones you're using at the time. So that's kind of nice. So what's interesting about the code that Audio Badger talks about is there is no i2s microphone input sound card built into the Raspberry Pi kernel. Why? They just haven't gotten around to it, or there's like a bug in it or whatever. I don't know the details. They'll probably add it eventually, just like they eventually added one-wire. Like one-wire is a kernel module to do one-wire support or I2C support. The first Raspberry Pi kernel didn't have I2C support. You couldn't use I2C devices. You had to enable it in the kernel or add a module. So we ended up compiling our own kernel just to do that. But basically they said, look, you know, for this i2s sound card stuff, we'll just, you know, we'll give you a chunk of code, and then what you do is you download the header files, all the information that tells you how to stick code into your kernel, and then you compile this little chunk of code, and then you say, like, insert the module, and you just kind of, like, poke it in, and, like, it kind of basically just works. And so if you're trying to develop modules, or you want to write your own, or you want to just load one for testing, you don't want to recompile your entire kernel, it's going to be an easy way to get the job done. Works pretty well. All right, so now that you're ready to join the Linux kernel team, so the code, so what's neat is actually there is a, let's see. Yeah, so this is kind of neat. So this is a source installer by Notro, who's just like pretty sweet. He kind of does everything. And basically what it does is it figures out what kernel you're using and then grabs the matching kernel headers for you. This is really great because people always ask me, like, oh, I want to do like a kernel module adaptation. I'm like I cross-compile on a Ubuntu machine, it's a virtual machine, and like Vagrant, and like it's a pain. This is actually a lot easier, and on a Pi 3, it's pretty fast. So you can just grab our Pi source from Notro, grab it, run the Python code, and it will do all the work for you and give you a the latest, the matching Linux in the file is called, the file, the reason it has like -3FOF35EE51111609, all that's the SHA hash that matches the GitHub commit. So it'll grab the right version for you. And then if you follow the instructions, I won't do because I've already done it. You basically create a new file called ASOC simple card. And it's basically a very simple sound card that has I2s input and output, and you can compile it with a very simple make file, and it just compiles with reference to the /lib/modules build, and you are pretty much good to go to create a .ko, which is a kernel object. So now once you've built the kernel object, you just install it with ASOC simple card, sudo insmod insert module, ASOC simple card ko, it installs, and like nothing happens. And then you can do, I think, lsmod. lsmod will list all of your installed kernel modules, and what's neat is you can actually see all of the kernel modules that you installed. So ASOC simple card, okay, we just did that, it's about 7K. And then you can see all the other things like SPI takes 7K, and then like the sound core in general is like kind of huge. GPIO mem, watchdog timer, SPI, config 802.11, so it's the an RF kill. This is part of the built-in Raspberry Pi WLAN stuff. i2c, IPv6, so all these kernel modules. Okay, and then once you've done that, you can go to loader. I actually didn't even look really into what loader does. Yeah, I'm not sure exactly what this does. I think it actually kind of makes the hook between ALSA and the sound card. Not sure exactly. I guess it's like, yeah, I don't know, the setup. Anyhow, you compile this also, and you also get a loader.ko, and then you do the same thing, sudo insmod loader.ko, and then you can do lsmod, and it's like, yeah, you've got your loader. I don't really understand the loader thing. I gotta look into that. Anyways, once you've done that, you can do a play L, and it will tell you, hey, you have a new card, Sound RPi Simple card. And if you do a record L, it'll say, yeah, you have a hardware capture device too. It's a simple codec. So like you're good to go. So every time you reboot, you have to do those two things. Eventually, you know, if you want, you can put that in your Etsy modules and put it into your kernel module directory, and it'll happen automatically. But for now, we're gonna do this. Also, one thing is you don't have any control. So that's one of the things with i2s. There's no audio control, so you can't change the gain. You can like create an ALSA device that acts as a mixer, but like I don't actually know ALSA, so I'd have to learn how to do that. But you do still have your main mixer. So card number 0 for ALSA, your main playback is still, in this case, my 3.5 millimeter audio out. So the audio input is i2s, audio output is 3.5 millimeter. You can change that to be, you know, HDMI if you want. So now I'm ready to record. So can you go back to the overhead? This was, it's not changing, which is okay. I actually don't need it to change.
Oh.
Yeah, this is the old image, but the image is updating here.
That's interesting.
Yeah, it's not a big deal.
Well,
Okay.
did you freeze frame it on accident?
I don't think no, because it's still replying. It's still doing something.
Here, unplug it and plug it back in.
Yeah, sure. Why
Yeah,
not?
see what happens.
Hey, that's always fun.
Yeah.
Unplug.
Anything change?
No. I actually don't really need it, to be honest. Yeah, whatever.
Is there a black hole near us or something?
Yeah, maybe.
I don't think there is. It's my 2.
It's HDMI out. Did it do something?
Try now. Anything? Nothing, huh?
No. Well, whatever. It's okay. Anyways, so
I'll get back to it.
it's not a big deal. So you wire up your i2s microphone, and then I need to get my a record. Okay, so this. So you can record from the command line. Of course, if you have software that uses ALSA, whatever, it'll get the audio device correctly. So in this case, we're saying, look, I want device number 1, not device number 0, because it's like card number 0 is the built-in, and card number 1 is that fake sound card. C1, 1 channel, mono, because I only have one i2s microphone hooked up. Record at 48 kilohertz. The file type is Sign16 little endian. This is just kind of like a magic setup. You should just always do that. Type wave V mono. I like this. This gives you visual feedback. And then V file.wave that tells you, I guess, where to output. So you want to maybe try this out. So I'm going to hit record on this, and then I'm going to kind of bend around. So you're not going to see me as I yell into the microphone. I'm yelling into the microphone. But hopefully you saw the thing go back and forth. Anyways, so now we have a file.wave that I just made. and I'm going to play it. And I'm going to, when it plays out, it's going to play through my.
Here, see if it's.
Oh, hey! Whatever you did, that was magic. It's going to play out through these speakers. So let's try this. A play file dot wave. Oh no, it didn't work. Why didn't it work? Hold on. Let me test my audio out because I did reboot. Did I change? Oh, you know what? My microphone wasn't powered. Hold on. You have to connect ground to ground in these here parts. Okay, let's try again. Well, this time I'm going to like tap on this. Yeah, okay, so that's working. Okay, I'm yelling into the microphone again. And then a play. Okay, I'm yelling into the microphone again. Okay, I'm yelling into the microphone again. All right, so proof that it works. And so next step, what you can do is you can wire up a secondary mic. So maybe I'll do that. It'll take me like 2 minutes. Just wire this up. People can watch. So you get another mic, like so. And then kind of you can put it next to it. Actually, it doesn't mean next to it. It can be far away. And then we'll just mimic the power wire. And then ground. And then the next couple pins, so there's data. And data, you're going to share that line. Because, sorry, the data line gets shared. We're going to skip that. Bit clock is the same between the two. Word select, that is going to be the same. And then you have that select line, right? Because we're like, you have to select which is the left and which is the right. So when we go to a record, and let's say we want to do stereo. So we do 2-channel, and then here we'll say stereo. You'll notice that if I tap the microphone, it's like on the left. Oh, can you go to the computer? Sorry. When I tap the microphone, it's the left bar that's it's right here. That's left, and then this is right, but there's nothing. And that's because of the select pin. So let's check it out on the oscilloscope. Why not? Let's see, this is B clock, select data. Okay, so it's kind of neat is actually nothing happens while it's not recording. You actually have to turn on recording to get data out. And so see how there is, when the word select pin is high, there's no data. And then when the word select pin is low, actually it's, hold on, let me sync on the, hold on. Got a trigger right. Okay. When the word select pin is low, you get data. And then when the word select pin is high, it's not doing anything. And that's because, again, the microphone, it's mono. There's only one element. If you want 2 microphones, you have to tell them one sends data at this point and one sends data at this point. And you can do that by toggling the cell pin. So let me connect a wire from the select pin. And hold on, the select pin, which is the rightmost pin. And then let me see what happens if I connect it to power. Okay, so let's go back to the scope, and I'll switch between the two. So now you've got word select pin high, data out. If I change that select pin back, it switched. So see, it's like back and forth, back and forth. And by default, it's the same as if it were low. Like default, the select pin is pulled down. So when we set up our other microphone, all I have to do is share that data line and then make sure that the select line is pulled high. So I'll do that right now. So the first thing you do is wire it up. So select line is high. And then we will share the data output. Oh no, hold on. I seem to have crashed my computer. I think the Raspberry Pi. I think I shorted power to ground by accident. All good. I will reboot. Okay. So, yeah, I totally pissed it off. Okay, reboot your Raspberry Pi. Okay, good, it's booting. Meanwhile, it's a good time to go to Mr. Ladyada.
Really?
Yeah, why not? You got these machines.
This is a Samsung 41. It does 40,000 components per hour. We also have a Samsung 482 that does about 40,000 components per hour. We have some of the larger components on one of them, and they work together. There's a computer that they're both plugged into, and they share the job, and they split it between two different machines.
Thank you for speaking for the machines. All right, I rebooted my Raspberry Pi.
Okay.
Okay, so back to the Raspberry Pi. We actually have to go back and mod those things because I have to restart because I connected power to ground. Good times. Sudo insmod loader the KO. Okay, and then I just want to check my also mixer. And we're almost done. Yes, it's good. Okay, so now when I do a record stereo, you see there's actually left and right channels. If I tap on this one or I tap on the other one, you get audio coming out of each one. And then if you go to the the oscilloscope cam, you'll see now we have data coming on the low clock and the high. So there you go, stereo audio in. That's not so bad. So this is good. Now that I know it works, I feel confident about getting these PCBs made, and then I'll do a write-up on how to do this yourself if you want. Hopefully the Raspberry Pi team will eventually add all this into the kernel, and it'll be just sort of like a device tree overlay. Super easy thing. That's it. That's my demo.
That's tonight's show?
That's tonight's show.
Okay.
Didn't we learn a lot?
We learned a lot.
We learned a lot.
Okay. Well, Desk of Ladyada is supported by the person out there who could put something in the cart and then hit checkout.
Yeah.
That's how we do it.
That's how we do it.
Yeah. And don't fall into the trap of being certain and miserable without taking the risk of doing something creative. It'll be okay.
All right. Thanks, everybody, for watching this Desk of Ladyada. I hope you learned a lot about i2s microphones. And, oh, cool. It's like transparent to the screen. We're going to have more shows. We'll have our Wednesday show.
We might do something tomorrow, we'll see.
We might. Friday, we have Hack Chat.
Yes.
That'll be cool.
3 p.m. Eastern Time on hackaday.io.
Yep. So see you then if we don't see you before then.
Bye-bye.
Bye.